that the norm of pi is what? It's pi times pi bar, right? It's the product of the complex number pi and its conjugate pi bar, right? So that says that what's that say? This is pi divides the norm of pi, right? Excuse me. Yeah. Is that right? Can I do anything? Right. Okay. So he says it's always the case that pi divides some positive integer, namely its norm. And since the norm of pi is greater than 1, how do we know that? Well, it's a prime, right? So it's not a unit. So it must have norm larger than 1. And he says we can write it as a product of primes in Z plus, right? All right. And he says since pi divides n of pi in Zi, and pi is prime in Zi, we must have that p divides some pj by lemma 6.5. So since the Gaussian prime pi divides n1, p1, p2, pr, right? And you can look at those as, are regular integers also Gaussian integers? Yes, they are. So lemma 6.5 applies. And since that pi is prime, this implies that pi divides pj for some j, right? Which is what's being claimed here, right? Some positive integer, the Gaussian prime must divide it, right? Right. He says, as already noted, this lemma tells us that the prime factors in Zi of primes in Z plus will give us all Gaussian primes. Let's see here. Here are the Gaussian prime factorizations of the first 3 prime numbers. Let's look at it. 2 equal to 1 plus I times 1 minus I. 3 equals to 3. 5 is equal to 1 plus 2i times 1 minus 2i. So these are factors. This is in Zi, of course, we're factoring, right? So these are the prime factorizations of the first 3 primes in Zi. How about 7? You're like, yes, please do my homework, right? Is 7 prime in the Gaussian integers? So there's no way to write 7 as a sum of 2 squares. So 7 is its own factorization. How about 11?
3 plus 10.
So
4, so that means you need 7, which is also no.
So it looks like 11's a no. How about 13?
We got 4 and 9.
Right. So what's the pattern here? Well, here's theorem 9.2. Theorem 9.2 says p in the positive integers, all right, prime p in positive integers is composite in the Gaussian integers, what? If and only if p is equal to a squared plus b squared for some a and b in the integers, all right? The proof of that, actually, I'd like to cover, but we should go on, and I want to at least state the main results today, and then I'll think about whether or not, I should show you the proofs in class. Corollary 9.4, it says that if P in the Gaussian integer is prime, all right, has P congruent to 3 mod 4, then P is not equal to a squared plus b squared for any a, b, and z. So congruent to 3 mod 4. So think about this. You have the one even prime. This is its Gaussian factorization, right? It's composite. All other primes past 2 are odd, right? So odd numbers, if you think about it, they fall into one of 2 classes. They're congruent to either 1 mod 4 or 3 mod 4. Those are the two cases, all right? 1 mod 4 or 3 mod 4. 1 mod 4 would be 5. 5 is 1 mod 4. 13 is 1 mod 4. 7 is 3 mod 4. 11 is 3 mod 4. This is not an accident. See, that's what this theorem says. It says this pattern continues. Anytime you have 3 mod 4, that prime in the integers is also prime in the Gaussian integers, right? But if your prime is congruent to 1 mod 4, you can write it as a sum of squares. And as such, it's composite in the Gaussian integers. That's the theorem. That's how you can decide a lot of the questions in your homework. It's just that. It's prime in the Gaussian integers if it's congruent to a regular prime is prime in the Gaussian integer if it's congruent to 3 mod 4. Otherwise, it's composite. Unless it's, well, otherwise it's composite actually because 2 is also composite, right? So, but his proof, I would say, Theorem 9.6, it says that there's the following conditions are equivalent: p equals to 2 or p equals to 1 mod 4. The congruence, x squared congruent to minus 1 mod p as a solution, and p equals a squared plus b squared for some a, b, and z. It says that these following conditions are equivalent. The proof of 3 implies 1 is in the paragraph right above the theorem, 9.6. And then on the next page, he has the proof of 1 implies 2 and 2 implies 3. The proof of 1 implies 2 is really interesting. And if you've read Stilwell, it really looks quite different. Stilwell uses an argument which is due to Dirichlet, and he uses Wilson's theorem. In contrast, the argument that's given on page 33 is based on a polynomial factorization and a really kind of slick polynomial factorization argument. It's really neat. But let's see here. And then finally, Theorem 9.10. Theorem 9.10 answers the following question. It says, an integer greater than 1 is the sum of 2 squares, all right, exactly when any prime factor, which is congruent to 3 mod 4, appears with even multiplicity. So you could still have a 3 mod 4 factor and still have it as a sum of squares. It's just you have to have pairs of them. Let me show you how this works. It's like 2205 is 5 times 9 times 49. So like 5 is a sum of squares, right? 49 is a sum of 9, but 9 and 49. Well, 9 is 3 squared. 49 is 7 squared, right? 3 and 7, them's primes. But how this works is just this. So you got like 1 squared plus 2 squared, right? Times 3 squared times 7 squared, and you multiply it in. And you've got 1 times 3 times 7 squared plus 2 times 3 times 7 squared. So that is 21 squared plus 42 squared. So that's how Theorem 9.10 works. That's why you have to have even multiplicity on any of the congruent to 3 mod 4 terms. Otherwise, you wouldn't be able to bring them in. If this was not 49, if this was just 7, this would all fall down because you'd only have 1 7, and you can't put you can't pull 1 7 inside a square. You can pull a square root of 7, but that's outside our world at the moment. you know? So, anyway, I'm sorry, I'm out of time. I tried. Is that enough? Can we go on? It's enough. I mean, the proofs at the end of the blurb are they're really quite nice, and I've spent many hours looking at them, so it saddens me that I'm not lecturing on them. But for the greater good, let us go on.